Hi all, happy Monday. Welcome back after the weekend. I will give you guys your quizzes back on Tuesday. So today we're going to talk about our second day of the normal distribution. We started this on Friday. So remember, when you watch these videos, please pause me when I ask you to try an example and check your work. Of course, you can always pause, revert, or rewind and go back if you're having a hard time understanding some concepts. So I'd like you guys to start with the warm-up. So go ahead, try those two problems out, and remember that this corresponds to what we did on Monday. And remember, once again, pause me and check your work when you're done. Okay, so here are the answers. Remember that the mean always goes in the middle, and then you count out 1, 2, and 3 standard deviations away from the mean in each direction. That's why I have 50 in the center on the right, and then I counted out 8 in each direction 3 times. Now also, please recall that we do have the possibility of falling outside of 3 standard deviations away. There's only a 0.3%, meaning 0.15 on each side of our normal curve. So based off of what we see there, now we can go ahead and fill out a couple percentages. So the first one says, using the example from above, what percent of the data falls within each interval? So 42 to 58, well, those are both within 1 standard deviation away. So that would be our first one, which is 68%. Greater than 34%, so that would be this and everything to the right. So that would be, you could either take 100 minus this area, which is really minus the 2.35 minus the 0.15, to put us at 97.5%. Or, of course, we could add up all these probabilities to the right. And then last but not least, less than 50. Well, less than 50 puts us at 50 and everything to the less. And since that's right smack dab in the middle, that would be 50% of our data. Example 2, we're going to be looking at percentages again. Remember that the big post-it is on the left-hand side of the board, if that helps you get those percentages, since I can't zoom into both at the same time. So here, go ahead and label your curve, pause me, label it, check your work. Alright, so once again, the mean's in the middle, and then I added 2.5, added 2.5, added 2.5, and then subtracted 2.5 3 times. So what percentage of males are over 72 inches? Well, that would be 13.5 plus 2.35 plus 0.15, which equals 16%. What percent are between 67 and 74.5 inches tall? So in that case, between 67 and 74.5. Well, from here to here, it's 68%, and then we have an additional 13.5%. So we're going to go ahead and add those two to get 81.5%. And then last but not least, our last one wants to know, in a group of 2,000 men. So this one is a little bit newer to us. How many would we expect to be taller than 6 feet? So 6 times 12 is 72. So if you're taller than 6 feet, that would put you here and everything to the right. So first we want to figure out what percentage of people that is. Now we actually already did that in part A. So we said that that was 16%. So we want 16% of 2,000. So grab your calculator and go ahead and type in 0.16 times 2,000. And you should get that 320 men out of 2,000 would be taller than 6 feet. You guys go ahead and try out the next example. So I have the normal curve for you. Go ahead and label the mean and then count your standard deviations. Answer A, B, and C, and then check your work. Go ahead and pause me now. Alright, so once again, the mean's in the middle, and then I counted out 3 standard deviations in each direction. So to be above 180, you're in that 2.35 plus the 0.15 to get us to the 2.5%. Alright, when we go ahead and flip it over, we want to know how many scored of the 250 students, how many scored above a 135. So above a 135, we're looking at all of these people. So that would be 84% of people scored above the 135. So we want 84% of 250. So 0.84 times 250, 210 people scored above 135. Lastly, if 13.5% of students received a B on the final, how can you describe their scores? Well, B I would say would be above average. The 13.5% corresponds to being between 1 and 2 standard deviations above the mean because we want to be above average. So if we go back to our picture on the first page, that would put us, that 13.5% would put us right in this region. This is our 13.5%. That would be above average. So I would say that those people who scored a B scored between 165 and 180 points. Alright, the next example is about tomatoes. So to win a prize at the county fair, the diameter of a tomato must be bigger than 4 inches. So we know that these are normally distributed, so that means that our probabilities apply. We know the mean of these tomatoes is 3.2 inches and the standard deviation is 0.4. So we want to know what's the probability that they're a winner. So if we draw this curve, we know that 3.2 goes in the middle, and then I can count out 0.4. So we get 3.6, 4, and 4.4. I don't really care about the stuff to the left. You can draw it. We're just using this to help us with the problem. So we want to know what's the probability that it's greater than 4. Notice 4 is a perfect 1, 2 standard deviations above the mean. So if we're greater than 4, that means that we've won at the county fair. So we want to know the probability of that. So that would be that area that's 2.35 plus that outer tail, giving us 2.5% of tomatoes could be a winner. So notice that everything that we've done so far has been a perfect number of standard deviations away. It falls exactly 1 or 2 or 3 standard deviations away. That's not always the case. So in like this example, we could have a tomato that has a diameter of 4.25 inches or a diameter of 3.15 inches where it's not a perfect number of standard deviations away. So that's why we have to have a formula and a way to find z-scores. We also want to make sure that we can interpret them. So in a continuous distribution, so remember that we know that our data can take really on any value, z-scores can take on any value as well. So even though when we have a z-score, our mean would be 0 because it deviates 0 from the mean, and then we count out 3 standard deviations in each direction, we really have a continuous curve. This really does go on in each direction. It's just very, very unlikely to have a z-score bigger than 3. So we count out our 3 standard deviations in each direction, and that's what a z-score is. So we could have a man that's 73 inches tall. So if we go back and we look at a man who's 73 inches tall, notice that that would put us in this range right here. 73 inches tall is not 1 standard deviation and not 2. It's somewhere in between those 2 standard deviations above the mean. So we just said he's bigger than 1 standard deviation, but smaller than 2 standard deviations. Because once again, z-score is the number of standard deviations, or the number of tick marks you are away from the mean. So let's go ahead and figure out exactly what this guy's z-score is. So what we do is we use this little formula. Z is x minus mu over sigma. So x would be the guy's height. So the height. Mu is our average. We've been using x bar up until this point. Mu is just our Greek letter that's basically saying the same thing. Sigma is our standard deviation. So if we take z, this individual's height was 73 inches. Our mean, on the other hand, we need to go back for a second. Let's take a look. So our mean was 69.5 and our standard deviation was 2.5. So let's go ahead and fill those in. Our mean was 69.5 and our standard deviation was 2.5. Now we go ahead and plug this into our calculator. When we plug that into our calculator, we get a z-score of 1.4. That means that this man was 1.4 standard deviations above the mean, which corresponds to what we said up here. We said he was bigger than 1, but less than 2 standard deviations away. So it makes it for a little bit easier comparison, and we also can figure out probabilities that correspond to that as well. But that's for, say, for a different class if you take more statistics. So what we're going to do is we're going to do one last example looking at z-scores. So a professional sports team looks for 2 main characteristics. We look for speed and strength. The mean time to run 40 yards is 4.6 seconds and the standard deviation of 0.15. So that's for running. The amount of weight lifted has a mean of 310 and a standard deviation of 25. Remember that a faster time is more desirable. So here we would want a negative z-score for running. The faster means that less time, so you would be to the left of your mean. Strength, however, we want to be stronger, so here we would want a positive z-score. And these are of equal importance when we're trying to pick between players. So what we're going to do is we're going to go ahead and we're going to get 4 z-scores. We're going to get player A's z-score for both time of running and weight lifted, and player B's. And then we'll go ahead and compare where they're at. So over here, we're going to take player A. We know player A's time to run. So we're going to do the z-score for running. So we're going to calculate player A's z-scores. So for player A, we take a look and we notice that they ran 4.42. It took them that many seconds to run 40 yards. Now remember the mean from the original problem was 4.6 and the standard deviation was 0.15. So let's go ahead and plug that in our calculator. And we get a z-score then of negative 1.2. Which remember is good because that means that they are actually faster than average because they have a negative z-score. Now we're going to go ahead and do it for their amount of weight lifted. So this player lifted 370 pounds from the original problem. 310 was the mean and the standard deviation was 25. So we're going to go ahead and type that into our calculator, and they have a z-score of 2.4. I would like you to pause me, and I would like for you to do the same thing for B. So figure out their z-score for their time running and the amount that they can lift, and then we'll talk about the comparison. That'll be the last thing we talk about. Okay, so please check your work. Pause me if you need to take notes and adjust. But player B, their z-score for running was negative 0.2, and their z-score for lifting was 2.6. So what we're going to do is we're going to go ahead and compare between the two. So I'd like for you to pause me, and I would like for you to look at this and decide who you think would be the more desirable player. I did draw a little diagram right here at the bottom to portray their z-scores. So over on the right is the amount of weight that they lifted. Over on the left is the time that they ran. So go ahead and take a second, decide who you would pick, and then we'll compare answers in just a moment. So pause me, make a decision, and explain why. So I chose player A, and the reason that I chose player A is player A is significantly a better runner. They are further from the mean, whereas player A is further from the mean and a significantly better runner. Notice that player B is the better weightlifter, but only by a little bit. So the differential is not much. So I said player A would be better because they are much, much better runner and they're only a little bit better at weightlifting. So if you need to go back, review any of the notes, just do that on the YouTube video. You should at this point go up to the sub and show them that you have completed the note sheet, and they will give you the homework worksheet, so you can go ahead and work on that. If you finish early, you can work on homework from other classes, or you can start working on that final review, constructed review packet, or your Math Excel. So I hope that you guys have a great afternoon, and we will see you tomorrow.